Okay, folks, so today I want to go over with you the last section of chapter 4. It is a rule called L'Hopital's rule, and it is the last kind of application of derivatives that we are going to do. And what L'Hopital's rule does is it brings us back to some limits that we used to not be able to do, and I used to say, oh, you're just going to trust me on this one, and we had some kind of, I don't want to say sketchy strategies for these back in chapter 2, but now that we know how to take derivatives, we can address these types of limits in a much more mathematical way. Okay, so if you take a look at this first limit, this is, nothing bigger than a limit that we would have seen in chapter 2 or back in when we were doing limits so long ago. If we plug 0 in, if we try direct substitution here, we get the square root of 1 minus 1, which is 0, over 0. Now before I would have said to you, oh geez, we're in trouble. Now we have to kind of say, all right, well, which one's going to 0 faster? Okay. But now we actually have a way to evaluate which one is going faster, which one is approaching 0 faster. In other words, we have a way to evaluate the rates of change of functions now. So that's what L'Hopital is going to do for us. So if you take a look at the graph, we can very clearly see that this thing has a limit. That limit exists. As you approach 0 on this function, it's a value somewhere between 0 and 1, looks to be right around 1/2. So 0 over 0, we know this is an indeterminate form, but it's got a value. We just need to get at it. And again, right now, we don't really have a method to do that yet. Well, this is, if we were in chapter 2, if we wanted a real value for that, we would have had to just go to the calculator and cheat it. Okay. But not anymore because we have our friend L'Hopital. All right, so L'Hopital's rule seems like magic, but it's not. All right, so first things first, you have to have two differentiable functions. So L'Hopital's rule is only going to work on rational functions where you have a function over another function, so like f over g or g over f. The other thing that has to be true for L'Hopital is that you have to either have both of your functions equaling 0 or both of your functions equaling infinity. In other words, you have to either be getting a 0 over 0 or an infinity over infinity. So if you remember, there are 7, I don't know if we talked about this, 7 indeterminate forms. These are only 2 of them. Okay, these are the only 2 that L'Hopital addresses. If we see another type of indeterminate form, we're going to have to do some wiggling because these are the only 2 forms of indeterminate forms that L'Hopital will address. So as long as you, when you go to evaluate a limit, if you do direct substitution and you come up with 0 over 0 or infinity over infinity, as long as your functions are differentiable at the value that you're trying to evaluate it, then you can use L'Hopital. Okay, so here's what L'Hopital says. Okay, it looks a mess, but just bear with me for a minute. It says that if these things are true, then, in other words, if this is 0 over 0 when you evaluate it or infinity over infinity when you evaluate it, then it is true that if you take the limit, not of the functions themselves, but of their derivatives, of their rates of change, you can then reevaluate and get an answer. Right? In other words, these 2 things are equivalent. So think about this. If these 2 things are both going to 0, and we saw this in chapter 2, like how about e to the negative x? We know that's going to 0 as x approaches 0. Let's assume x is approaching 0. And x squared. That's also approaching 0. Okay. In chapter 2, back in the day, we would have said, okay, yeah, but which one's approaching 0 faster? We know that e to the negative x is going to approach 0 faster than x squared, so we would say he wins out, this thing is going to be 0. Right? This is the technical way to do that. When I say who's approaching 0 faster, what I'm really talking about is those functions' rates of change. Now, it is important to notice here for L'Hopital that we did not in any way, shape, or form use a quotient rule. And this is never, ever, 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 ever to be confused with a quotient rule. all you're doing when you do L'Hopital is instead of comparing the two functions, you're comparing their derivatives. You're not taking the derivative of the rational function. You're just getting the rate of change of f of x, the rate of change of g of x, and then doing a comparison of those. This is not the quotient rule. It's derivative of top, derivative of bottom. It's what we dreamed the quotient rule would be, but that dream never came true. Okay, so here's my translation, which I've pretty much already said, but if you're writing stuff down. So if the limit of f of x over g of x is producing for you either a 0 over 0 or an infinity over infinity, that's important. That's an if. Okay, so two things. It's got to be one of these two things. If it is not producing a 0 over 0 or an infinity over infinity, and you L'Hopital anyway, you can potentially get a wrong answer. Right? So do not, under any circumstances, L'Hopital unless this condition is met. This is an if your limit is producing one of these two indeterminate forms, not just any indeterminate form, but these two. Then we can attempt to fix that by taking the derivative of the top and the derivative of the bottom and then reevaluating the limit. But again, if and only if you have these two, one of these two specific indeterminate forms. If you do not have a 0 over 0 or an infinity over an infinity, you may not apply L'Hopital. Could it happen that you stumble on a correct answer? Yes. Would you get any credit for it? No. If you are L'Hopitaling at an inappropriate time, you will not get any credit for it at all. Okay, so let's take a look at these two. We looked at this function back in the day, and I told you that you just had to trust me. I said, let's look at the graph. We'll see what this limit is. Because if I plug 0 into sine x over x, I get a 0 over a 0. And we knew way back that's no good, right? So we went and peeked at the graph because there wasn't really anything algebraically that we could do about it, right? Now, I can do something about it because now, since I'm getting a 0 over 0, I can call upon my friend L'Hopital. There he is. He's a handsome devil, isn't he? All right, so when I need L'Hopital, I'm going to rewrite my limit. I'm going to do the limit as x approaches 0. Instead of sine x, I'm going to do its derivative, cosine x. Instead of x, I'm going to do its derivative, 1. And I'm going to reevaluate this limit. So as x approaches 0, the cosine is now approaching 1 over 1, and I get a limit of 1. Look at this. Boop, boop. There it is. It really seems like magic. Okay, now, down here, as you approach infinity, sine x, this is a little dicey here, right? Because as you approach infinity, sine x is oscillating. We know this, right? But the one thing we do know is that the sine x is oscillating only between -1 and 1, right? It's never going to go lower than -1. It's never going to go higher than +1. So as I approach infinity, I don't necessarily know what my derivative is, but I know one thing, or my y value is, but I know one thing, and that's that it's only ever going to be a number between -1 and 1. Okay. Now in the denominator, x is flat out approaching infinity. So notice here, this is not an indeterminate form. Okay. This limit I can do. I do not need L'Hopital here. That just flat out comes out to 0. I've got a finite number in the numerator. I've got infinity in the denominator. So I am dividing a finite number, a small one at that, by infinity. That's going to approach 0. You cannot L'Hopital here. If you L'Hopital here, you will get the wrong answer. Okay. Let's take a look at another one. I do not believe we looked at this one at the beginning of the year. All right, so here I have the limit, and notice I'm coming one side for the left and one side from the right. If you look at the graph as you approach 0, you will see why that is. We are going to get two different answers. So if I approach from the right, if I approach from the left, this is from 0, 0 from the negative side. Okay, so if I approach 0 from the negative side, sine x is going to come out to a very small number approaching 0, but it will be negative. X squared, on the other hand, is also going to be approaching a very small negative number, but I'm going to square it, so it's going to end up being positive. Okay. So the fact that I have a very teeny tiny number that is approaching 0 on the top and the bottom means I have an indeterminate form. The fact that one of them is negative and one of them is positive really means absolutely nothing to me. So I need to call in my buddy L'Hopital. All right, so let's take our derivative. I'm still going to be doing the limit as x approaches 0 from the negative side. The derivative of sine is cosine. The derivative of x squared is 2x. Okay, so let's do this again. As you approach cosine from the, on cosine, as you approach 0 from the negative side, so teeny tiny negative numbers, we'll get a 1. Down here, teeny tiny negative numbers put in here are going to produce teeny tiny negative numbers. In other words, negative 0. In other words, an extremely small number, yes, but a negative one. And that's important because when you take a finite number and you divide it by increasingly tinier and tinier numbers, you're going to get an infinity. But it's going to be infinity if you're dividing by positive teeny tiny numbers. Here we're dividing by negative teeny tiny numbers. So this is going to come out to a negative infinity. And we can see that in the graph. Write down the negative infinity. Okay, now over here, the same thing is going to happen. We're going to need L'Hopital again. We're just approaching 0 from the other side now. So now I'm going to get positive numbers out of sine and positive numbers out of the denominator. It's still a 0 over 0. I'm still going to need L'Hopital. So I'm going to do the limit as x approaches 0 from the positive side. Again, the derivative of sine is cosine. Derivative of x squared is 2x. And we reevaluate. Okay, I'm still going to get, whoops, I'm sorry. I'm still going to get 1 out of my cosine. But now I'm going to get a positive teeny tiny number in the denominator. 2 times a tiny, tiny positive. And so this one's going to come out to positive infinity. And again, you can see in the graph. All right, so I found this graphic on the internet a few years ago. And I just, I don't know, I think it's an interesting illustration of L'Hopital's rule. It says indeterminate forms are like tug of war. Which side wins depends on which side is stronger. And this goes back to that idea that if I have, you know, the limit, if I have, oh my, we're really going to do this again, huh? Okay, if I have the limit as x approaches infinity, let's say of e to the x over x. Technically, this is an infinity over infinity, right? Technically, this is a L'Hopital. But back in the day, what we would have said was, look, e to the x grows so much faster. It's tugging so much harder than x. This is going to infinity, and so is this. But this is like flying to infinity, and this is just kind of like taking a stroll to infinity. Now, L'Hopital is going to flesh that out for us. If we use L'Hopital on this, we're going to get e to the x over 1. We reevaluate it at infinity, and it goes to infinity, right? And if you're on the AP, you would have to do that, right? But sometimes you can look at them and just kind of know what's going to happen based on this idea that e to the x is tugging to infinity, and x is also tugging to infinity, but in the end, e to the x is pulling a lot harder, so it's going to win. So in other words, your numerator is going to win out. Right? So I don't know if that helps you think about it, but I thought that was a little interesting illustration of it. Okay, so let's talk about what AP requires you to say when you are faced with a problem that requires L'Hopital. Okay, this is very much like your value theorems, where you have to state your theorem and you have to state your criteria. And then from there, draw the conclusion that your rule gives you, right? Years ago, we used to just be able to do L'Hopital. And then a couple years back, they said, just kidding. We want to treat it like a value theorem. Now you have to state it. So when you are doing your L'Hopital problems, just like when you did your value theorems and you had to say, since it's continuous on a closed interval, and since this is true, MVT states that this is true. We have to do the same thing for L'Hopital. So the first thing that we have to do is evaluate our limit and show that we're getting a 0 over 0 and infinity over infinity. Okay, then we have to specifically say, since f of, let's say the limit's approaching 2, since f of 2 is equal to 0 and g of 2 is equal to 0, or it might be that they're both infinity, right? So since f of 2 is equal to infinity and g of 2 is equal to infinity, although I'd say approaching infinity there, okay, we state the rule. So since this is true, in other words, this is my condition, L'Hopital's rule states that, and this is L'Hopital's rule. You have to write it, right? If they gave you f and g, then this will be f and g. If they gave you h and k, then this would be h and k. But you're going to say that this limit that you gave me that came out to 0 over 0 or infinity over infinity is equal to this limit with the derivatives taken. You're going to show this, right? And then you can say, therefore, and fill it in. This limit is equal to this limit, and then evaluate it. But these 3 parts have to be there. So I want to do a couple problems with you where I actually go through what you really have to write and not just of the calculation of L'Hopital's rule. Obviously, if you see L'Hopital on a multiple choice problem, go for it. You don't have to write statements out. But if it shows up on an open-ended, you got to write the statements if you want to get the credit. They will not give you credit if you don't write this out. It's painful, but it's true. Okay, so let's take a look at this same problem that we looked at the beginning of the period, where before we would not have had a way to do it. So we know that this comes out to 0 over 0. So if we're on the AP and this comes out to 0 over 0. Okay, we're going to say, since the square root, well, sorry, I already messed up and I'm not even like a second into it. One of the things that I would do is I would go like this. Say, hey, AP, just for the sake of my own sanity, I'm going to call this f of x and I'm going to call this g of x. Okay, so I'm going to say that since the limit as x approaches 0 of f of x is equal to 0, and the limit as x approaches 0 of g of x is equal to 0. So I'm saying since this and this. Now, could you write since this limit is equal to this limit is equal to 0? Yes, but be very careful because with the infinities, sometimes you get a positive infinity and a negative infinity, in which case you would have no choice but to write them separately. You want to be careful of stringing them together unless they actually truly are equal. Okay, so since this is equal to 0 and this is equal to 0, L'Hopital's rule states that. Okay, so let's say the limit as x approaches 0 of this has to be equal to the limit as x approaches 0 of the derivative. So this is where we're going to apply our L'Hopital. So let's take our derivative. On the top, I'm going to have 1/2 1 plus x to the negative 1/2 minus 0, and then over 1. Okay. So if I simplify that, I'm going to get 1 over 2 square roots of 1 plus x. Okay, so therefore, the limit as x approaches 0 of this is equal to the limit as x approaches 0 of this, and that equals 1/2. And isn't that what we said it looked like? Did I put the graph on here for us? Yes, I did. Okay, look, there it is right there. We thought that that's what it was. Okay, but again, it's really quick to do the L'Hopital here, but you have to make sure you're writing out your criteria. So since this is true, L'Hopital states that my original limit is equal to this new limit involving derivatives. Therefore, this limit is going to come out to 1/2. Okay, let's take a look at another one here. Okay. So if I do the limit as x approaches infinity of the ln of x over 2 root x, the natural log of x is approaching infinity. It's doing it really slowly, but it's doing it. Down here I have 2 root x. So again, this is approaching infinity. Root x isn't approaching infinity particularly fast, but it is approaching infinity, and it's approaching infinity faster than the natural log. Natural log is the slowest growing function. So again, if we're thinking about this tug of war idea, I have something approaching infinity and something else. This one's approaching infinity faster. So think about what that's going to mean for our function. Okay. So I have an infinity over infinity, so I know I need to call upon L'Hopital. So let's write our statements. So since the limit as x approaches infinity of the ln of x is equal to infinity, and the limit as x approaches infinity of 2 root x equals infinity. So I've got both things equaling infinity. L'Hopital's rule states that. Let's write our original limit. Has to equal the limit of their derivatives. So the derivative of the natural log of x is 1 over x. The derivative of 2 root x would be 1/2 x to the -1/2. Okay, so we got some simplifying to do here. The 2's cancel, right? I end up with, this is a square root of x, but in the numerator, right? Because it's negative. And this is an x, but in the denominator. Look what I have. Infinity over infinity. But again, look, this one's going to infinity slower than this one's going to infinity, just like it was originally happening. These are the painful ones. We know the answer. We know the answer, but we have to prove it. Okay, so here's the problem. This is still coming out to infinity over infinity. So we have to do it again. Okay? We're going to have to restart ourselves. So since the limit as x approaches infinity of the square root of x is equal to, I'm going to do a shortcut way this way, the limit as x approaches infinity of x, and those are both equal to infinity, L'Hopital states that this limit is equal to this limit, the limit of their derivatives. So 1/2 x to the -1/2 over 1. I'm going to pop up here, because that's going to simplify out a little bit too. That's going to simplify out to 1 over 2 root x. And now when we put an infinity in, we get 0. Now I don't know about you, but I kind of predicted that in the beginning, right? Because I said this is going to infinity faster. So if this number is getting bigger faster than this number, this thing's going to go to 0. Right? But L'Hopital fleshed it out for us. Just have to do a lot of writing. So we can finish this off by saying, therefore, this limit, the original limit you gave me, ln of x over 2 root x, equals this final limit that we came up with, and that equals 0. And there's our final answer. Okay, so again, the mechanics of L'Hopital's rule aren't terrible, right? You know how to take derivatives. The hard part of L'Hopital's rule is writing out that argument, writing out that statement. Okay, so if you have any questions, I am around. If you go back into Schoology, you will see a very short assignment. It's 4 problems. 2 of them are just straightforward limit. They give you it. One of them, they give a table of values for you to pull some values of your function and your derivative from. Another one, they give you a graph where you have to pull the values of your function and your derivative from. But it's all the same, just they're all coming back to you have an indeterminate form and you have to use L'Hopital to get at it. Okay, next week we will talk about the other indeterminate forms and what we do when we're thrown one of those. All right, have a good day.